Hi, let us try another example related to the design of reinforced concrete pad footing. So far, we have done one example with the pad footing subjected to only axial load. Now, based on the same set of specifications, we're going to discuss about the design of the pad footing subjected to axial load plus the moment at the major axis. The purpose is to demonstrate the differences in terms of the calculation steps between the pad footing subjected to moment and not subjected to any moment. Without further ado, let us get started. In this case, we deal with the pad footing subjected to the ultimate axial loads of 1000 kN and the moment in the major axis of 150 kN-meter. It is assumed that the exposure class is XD2, which is subjected to chloride attack and it is always wet. We set the design life of 50 years. The FCK equals to 30 Nm/mm², concrete unit weight 25 kN per meter cube, bar strength 500 Nm/mm², soil bearing capacity 200 kN per meter square, the maximum size of the aggregate 20 mm, and probably the reinforcement bar of 12 mm in both directions. First, let us determine the nominal cover. The formulas for the nominal cover can be obtained from Eurocode due to C minimum plus the deviations. Under normal circumstances, the deviations it will be equal to 10 mm. As for the C minimum, it is governed by the bond, by the durability, and a minimum of 10 mm. C min bar here is equivalent to the size of the reinforcement, which is 12 mm. As for C min durability, you may refer to table 4.3n and also table 4.4n. The recommended structural class is S4 and you are referring to the exposure class XD2. The design life is 50 years. No changes to the structural class. The concrete strength is 30. Also no change to the structural class. The changes applied to the structural class, it will be when the design life is prolonged into 100 years, or if you are using higher grade concrete of more than 40 Nm/mm². In this case, no changes to the structural class. It will refer to the recommended S4 under the exposure class XD2, which is 40. The C minimum, it will be the larger value of the three. C min bar is equals to 12, C min durability equals to 40, and a minimum of 10 mm. That gives you C min equals to 40 plus 10 mm deviations. Your nominal cover will be equals to 50 mm. Next, we need to propose a suitable size of the pad footing. We are using the prescriptive methods for the design. According to the prescriptive method, and assume safe bearing pressure is used to determine the size of the pad footing shall be based on the serviceability limit state, which in this case, the loading givens are in the ultimate limit state. That means we need to do some conversions from the ultimate limit state into the serviceability limit state for us to determine the suitable size for the pad footing. With the given ultimate limit state loading, we don't know how much is contributed by the GK and how much from the QK. You know the factor of safety for GK is 1.35 and for QK is 1.5. Not knowing the quantum of the GK and the QK, we cannot use the factor of safety of 1.35 and 1.5 directly. Therefore, we will need to estimate the service load by dividing the ultimate load with the factor of safety of 1.4. Dividing the ultimate axial loads of 1000 kN with the factor of safety of 1.4, you obtain the service axial loads 714.3 kN. You will do the same for the moment. Divided with 1.4, you acquire the service moment in the major axis 107.1 kN/meter. Taking into considerations of the self-weight of the peg footing. However, at this moment, we still don't know the size of the peg footing. What we can do is to first assume the self-weight of the peg footing equals to 10% of the service load, and then estimate the required area for the contact between the peg footing and the soil. This is calculated by using this formula. 1.1 is due to the service load plus 10% of the service load divided by the soil bearing capacity, which in this case, the soil bearing capacity given is 200 kN per meter square. You obtain the estimated required contact surface area of 3.93. From here, you can use this as a guideline for you to determine the appropriate size of the peg footing. Bare minimum, you're going to propose a size with the contact surface area greater than the estimated value. In fact, you can propose any shape for the peg footing, square or rectangular. In this case, we have bending moment in the major axis. Due to the existence of the moment, normally we will choose to have greater length in the directions of the bending moment. In this case, bending moment is in the major axis. Therefore, we could try to have the major axis to be slightly longer than the minor axis. You can do try and error for any shapes, as long as the contact surface area is greater than what is estimated. However, later you will still need to check in order to confirm that the proposed size passes the design. The contact surface area is not the ultimate criteria for us to determine whether the proposed size is adequate. The reason being here is when you do the estimations of the area, this is on the basis that the peg footing is subjected to pure axial load, where there is no moment. However, in this case, you have moment. This moment later shall bring to the redistributions of the stress, leading to some areas of your peg footings subjected to higher stress, while some other areas with lower stress. This means that when this peg footing is subjected to moment, the stress is no longer uniformly distributed throughout the contact surface area. This is something unique to the peg footing subjected to the moment, as compared to the peg footing subjected to pure axial loops without any moment. To make it simple, if your pad footing is subjected to pure axial loop, you only need to make sure that the proposed contact surface area is greater than the estimated surface area. This is of course making sure that the estimated self-weight of the pad footing is greater than the actual self-weight. Now, in the case of the pad footing subjected to moment, you cannot fully rely on these areas to determine whether the proposed size is adequate. You will have to consider the effect of the moment on the soil bearing pressure eventually. So what you're going to do, it will be for you to compute the soil bearing pressures as a result of the moment. To do so, you will need to first determine the actual self-weight of the pad footing. Propose a thickness and the size of the pad footing. Get the volume of the concrete. Multiply the H, B and T, giving you the volume, and then multiply the unit weight of the concrete, which is equals to 25 kN per meter cube. That gives you the self-weight of the pad footing is equals to 72.6 kN. And then you look into the equations to determine the soil bearing pressure. You need the M. M is given. After converting to the surface moment, it is equals to 107.1 kN meter for the major axis and 0 for the minor axis. You need the Y. Y refers to the central axis of the rotational plane. By looking at your pad footing, there are two rotational planes. One is for the bending moment in the major axis, which is in this rotational plane. Another one, it will be for the moment in the minor axis, which is in this rotational plane. Let's say now we take this as the reference point. We will need to determine the locations of the rotational plane. Based on the proposed dimensions of the pad footing, the major axis have the width of 2.4 meter. The rotational plane will fall at the center of this 2.4 meter. That means your Y in the major axis, it will be 2.4 meter divided by 2, which is equals to 1.2 meter. We will do the same for the minor axis. The proposed size in the minor axis is 2.2 meter. The rotational plane, it will be at the middle of the 2.2 meter. That means you use 2.2 meter divided by 2, you have 1.1 meter. And then you need the I, which is the moment of inertia. The I here represents the moment of inertia of the pad footing against the rotational axis. The equations for the moment of inertia is BH power 3 of 12. You have two axes to calculate, and you will need to be very careful with the B and H. You don't have to memorize the equations. You can always solve it in the graphical manner. Let's say you refer to this diagram here. We are talking about the moment in the major axis. This will be your rotational plane. The dimensions parallel to the bending moment, it will be taken as the H. Now, when you need to calculate the moment of inertia, you will use B multiply H power of 3 divided by 12. That gives you the moment of inertia in the major axis. The B now here is 2.2 meter and the H here is 2.4 meter. Therefore, the moment of inertia for the major axis, it will be 2.2 meter multiplied 2.4 meter power of 3 divided by 12. That gives you 2.534 meter power of 4. Next, you look into the moment of inertia in the minor axis. The moment in the minor axis is rotating at the neutral axis of this. The dimensions of the column parallels to the moment shall be taken as the h. That means, to calculate the moment of inertia, you will use this multiply this power of 3 and the whole thing divided by 12. Specifically, you will use this multiply this power of 3 divided by 12. This gives you another value, which is 2.13 meter power of 4. The same formula applies to both the moment of inertia of the major and the minor axis, except the B and H swap. Now that you have the M, you have the Y, you have the I, you also have the axial load, the surface axial load, which is equals to 714.3 kilonewton. You also have the self-weight, which is calculated as 72.6 kilonewton. Now you need the contact surface area A. You will use the actual contact surface area due to the proposed size of the pad footing. Substitute the values into the equations. The moment acting onto the pad footings will give influence, resulting the increase of the stress in the major axis, whereas the other end of the major axis will have reduced stress. This leading to you the maximum soil bearing pressure equals to 199.8 and the minimum stress, it will be 98.3. Now if you calculate the bearing pressure in the minor axis, since there is no moment, the effects of the moment here, it will be equals to 0, leading you a uniformly distributed stress in the minor axis. Based on the stress calculated both in the major and the minor axis, check against the soil bearing capacity of 200 kilonewton per meter as given in the question. None of this stress is greater than the soil bearing capacity. Therefore, you will know that the soil bearing capacity is not exceeded and the proposed dimensions of the pad footings is acceptable. If you find your soil bearing capacity being exceeded, most likely due to the maximum soil pressures in the directions of the moment, now you will have to try and error with various sizes of the pad footing until you get the soil pressure here lower than the soil bearing capacity. This step is very important as it ensures the stability of the pad footing. You need to make sure this passes before you proceed with the structural design. Otherwise, no matter how strong you make the structure, if the soil bearing capacity is exceeded, the foundations will undergo settlement. Eventually, This is going to jeopardize the integrity of the entire structure, resulting the structures to fail. Once the dimensions are concluded, then you are good to go for the structural design. This shall be covered in the following videos. Stay tuned.